Welcome back, everybody. Today, we're pleased to have Aiden Bullish, who's a research scientist at Lawrence Berkeley Lab and a longtime collaborator with our research group and contributor to parallel graph algorithms, which is what he'll be talking about today.
Thanks for inviting me, Jim. This is a pleasure to be here. So as you might see, I have an accent and I have a bronchitis. So if you have trouble hearing me, raise your hand and I'll try to, adjust, speak a little louder than I do, or something like that. So I'll be speaking about parallel graph algorithms. And so I'll start with the regular definition about what's a graph. Essentially, a graph, in its simplest form, is a set of vertices that usually is used to model entities in a data set, and a set of edges, which is used to model the relationship between those data entities. And it's really simple picture. And M and N usually denotes the number of vertices and the number of edges, respectively, by convention. And the diameter of a graph is the maximum number of hops between any two pairs of vertices in a graph. Is going to be a useful measure of the span of a computation that we'll see later. So the edges in a graph can be weighted, unweighted, directed, or undirected, and there are spatial algorithms for different kinds of those graphs. And in fact, edges can have attributes, and then you can encode lots of auxiliary information in the graph by encoding those information on the attributes of the edges. Finally, another useful definition is a sequence of edges where the end point of the first one is the beginning point of the second one, and so on, is a path from U1 to UN, and the length of a path is the sum of all of its weights. So I'm going to start with applications today, and then talk about how to design parallel algorithms in general. And I will go over case studies. These are not random case studies that we picked. Pretty much all of them illustrates a technique to design parallel graph algorithms. For example, we will use the randomness for maximal independent set. And we will use recursion, parallel recursion for strongly connected components. And breadth search and shortest paths are so fundamental that I can't really have a lecture without them. So let's start with the applications. Probably one of the most useful application that you use every single day is routing. Every time you go to Google Maps, you open up, how can I go from one place to the other? It's essentially a routing algorithm that runs the shortest path query from point to point. And you can do this very fast thanks to parallel computing and smart graph algorithms. And that was basically a science paper that illustrates how it's done. Internet is very important. First of all, routing on the network layers is a shortest path algorithm in general. And the page rank, where you go to Google and rank web pages in some sort of graph ranking. And the classification on the web and clustering is also a graph algorithm. Specifically in scientific computing, where most of my interests lie in, graphs serve as very important building blocks for sparse matrix computations and preconditioning techniques such as incomplete factorizations or the support graph preconditioners. Some of you might have seen those things in the lecture. I don't know if, what percentage of them has been has been mentioned in this class so far. But pretty much every sparse matrix computation involves some sort of a graph underneath it. Lastly, probably very important these days, is the large-scale data analysis. I've said in my first slide already, graphs provide a natural abstraction where the data points become vertices and the relationships between data points become edges. How much they are correlated, what kind of relationship is that, and so on. And the sources of data can be pretty arbitrary. Astrophysics data, where you're modeling, OK, Airbus really wants to connect me, but I won't do it. Astrophysics data, where you're modeling different stars and galaxies as vertices and their interactions as edges. Bioinformatics data, similarly, and social informatics. I've talked a couple of those where every web page or person on Facebook will be a vertex, and every kind of interaction, whether you like a page or whether you're friends with some other person, will be an edge with random attributes. And then you can do all sorts of different computations on those. Another very interesting application these days is the analysis of the brain. The neuroscientists are analyzing brain connections, and they're increasingly more likely to use graph techniques, where the vertices are a group of neurons where we can't really measure single neurons at the moment. So we use something called a region of interest, where it's a clump of several thousand or millions of neurons together, and the edges is the functional or structural connectivity between those regions of interest in the brain. And the kind of questions where you can ask is, what is the deviation of these network properties from the ideal will tell you how much this person is susceptible to an important disease such as Alzheimer's. These are all correlations, but they're very helpful at the moment. And I expect a lot of a lot of advances on this field pretty soon. So how does research in parallel graph algorithms go? First of all, why do we do parallelism in these graphs? In most of the applications I've talked, the data sets are pretty huge. Astrophysics data sets, if you think about it, or social network data sets, we're talking about billions of vertices or edges. So that's pretty much the need for parallelism on graph algorithms. Here, this is a summary slide where the first column is the application areas, second column is the kind of graph problems, not algorithms, to solve, such as finding graph partitionings, matching, route planning. And the algorithms we use is on the third column, and finally they have to be mapped to parallel architectures. So really the research goes from, you can do it as a top-down approach. In this figure it's a left to right. Start with the application area, find the kind of problems that needs to be solved for the application area, what kind of graph algorithms are needed to solve that area, and how can I map them best to an architecture. And usually the data size and problem complexity determines what kind of problems you can solve. So this is probably another way of listing those graph kernels. I won't go into too much detail because it's a little verbose at this point. In fact, I'll go over designing parallel graph algorithms. I guess the history of graph algorithms in parallel goes back to the PRAM model mostly. If you do a literature search, you'll find most of the published algorithms analyzed in the PRAM model. The trouble with I guess everyone knows about the PRAM model?
We have talked
Yeah.
about not all the variants of it.
Yeah, so the PRAM model was a theoretical extension of the general RAM model, where it's a very powerful device, and it has the ability to model infinite number of processors. But as I will talk about in a second, it ignores most of the communication costs, which is the fundamental bottleneck in parallel applications these days. Well, the advantages are that they're really simple and clean semantics about how to analyze an algorithm in PRAM. And as I said, the literature actually is full of PRAM algorithms that are optimal in a sense, and they can be analyzed independent of the network topology. The downsides are essentially it's not a realistic model. All the communication costs are ignored. Processors go all synchronized, and the big O notation is susceptible to misleading you in terms of how much performance you're going to get in practice. So what are the building blocks if you're going to write a parallel graph algorithm on the PRAM model? Usually the algorithms are built on top of a few simple building blocks. They can be prefix sums, list ranking, Euler tours, tree contraction, and some of those might have been covered in this lecture, or at least on the previous versions of this of this class. But that's not going to be the focus of my lecture today. I'm going to be mostly talking about practical algorithms. As a personal perspective, the world runs on practical algorithms that are really bad in worst case. And I don't know what I can do. Perhaps I can turn that off, and then it won't come back again. That's the hope. So you can't really implement an algorithm without a data structure. So let's start with the data structures. The static case, which I'm going to be talking about mostly today, there's two main cases where the graph is dense or the graph is sparse. And when we say graph is dense, it really means that almost all of its possible edges and square pairs of edges are present. These are rarer in practice, but they have a very important set of applications, and I'm going to be talking about one particular dense graph algorithm, namely all-pair shortest path, which has a fundamental application in nonlinear dimensionality reduction. Sparse graphs are more common, usually in social informatics or actually scientific data sets. And you would store a dense graph probably in a matrix notation, what we call an adjacency matrix. For every pair, there is a matrix element. For sparse graphs, there is a couple of different choices. The textbook choice is what's called an adjacency list. And what's used more in practice for high-performance graph computations is a compressed sparse matrix, which is nothing more than a cached-efficient version of an adjacency list. So I'll see what it means. We'll see what it means in the next slide. For dynamic graphs, which I won't talk about much today, there's a lot of questions one needs to ask before answering what's the right data structure. First of all, a dynamic graph is defined as a graph which evolves over time. New vertices or edges are introduced or deleted. It depends on how fast those additions and removals of edges and vertices are. If they're infrequent, you can do a batch update. And if they're crucial in the sense that they change the result of the running computation with even a single vertex or edge update, then you would need to do really eager updates as opposed to waiting for batches. And what is the update rate determines what kind of data structures you can use and what kind of queries you're going to run on this application also determines. So that's a big field, probably a couple lectures by its own, and not fully established yet at the moment. Let's go back to the common graph representations. So this is the sparse matrix representation that I've talked about. So in this picture, you see a textbook adjacency list of the graph on the left, where there is an ON ON array that represents the vertices, and every single vertex has a list that lists all of the neighbors of that vertex. Simple. The trouble with that data structure, if you implement it directly, is linked lists don't have cache locality. So when you're going from one edge of 4 to the other one, another neighbor of 4, you might make a cache miss. So what's used in practice, compressed sparse rows, is essentially a concatenation of all the edge lists of the vertices together. So you'll see the duality immediately. What the resulting data structure in practice differs from adjacency lists only in two aspects. One of them is it's more cache efficient because it's an array representation. That's the upside. The downside is if you want to introduce an edge, you can introduce an edge here in O1 time, right? But you can't introduce an edge in the middle of an array in O1 time. So these are more static representations, but up to half an order of magnitude faster in practice. Well, that's for a serial representation. How about distributed? The simplest thing one can think of for distributing a graph over a parallel processor, a distributed memory parallel processor, is to have the first processor store n over 2, 1 to n over 2 set of vertices, and the second processor store the second n over p pieces. So each processor gets n over p vertices, and all the adjacencies, all the edges connected to that vertex go with it. So that's what's called a 1D partitioning. And the reason we call it 1D partitioning is if you look at the adjacency matrix of the graph, it's essentially dividing the graph in a one-dimensional manner. Well, that's all good, but I will talk about the downsides of those in the performance section a little later. That has the advantage of being extremely intuitive, but creates lots of load imbalance and communication issues. An alternative, which is gaining more traction, is a two-dimensional distribution. And again, the name two-dimensional comes from the fact that we're dividing the data structure, adjacency matrix, in a two-dimensional checkerboard fashion. It doesn't need to be checkerboard. It can be a different two-dimensional structure. As long as it's not divided by rows and columns only, is considered a two-dimensional decomposition. So this is a little harder to visualize in terms of the graph, and therefore almost always the matrix is used to describe the two-dimensional decomposition. It's quite hard to describe what set of edges are distributed to what processors. But in practice, it's not very important. So I will give algorithms for both one-dimensional and two-dimensional decomposition for breadth-first search and talk about differences in practice. But before that, let me summarize this section with a summary slide that says what are the things that one needs to care about when designing a high-performance graph algorithm. Essentially, some of those are no different than other parallel algorithms. You would like to minimize the number of synchronization points because it's not only time-consuming to actually do a synchronization on a big parallel computer, it also increases the load imbalance. If there's a little bit of load imbalance in the computation, things might balance itself out if you synchronize very loosely. But if you synchronize in every second, then you're essentially putting a checkpoint. And that's much more important in graph algorithms than dense matrix algorithms, where things are usually balanced in nature. Here, things are imbalanced by design. Of course, very important question in every parallel parallel algorithm is, where is the data? When you're designing a parallel algorithm, you would like to distribute the data so that minimizes the inter-processor communication. And finally, once we fix those issues, the high-performance questions become, how can I increase the locality, and how can I minimize the DRAM traffic within the node? But those are less about parallelism, but more about high-performance questions. And a question we will ask to ourselves frequently in every algorithm is this work efficient? Meaning that, is the parallel time times the number of processors equal to the serial work that needs to be done? There are some algorithms which are work efficient, but we will see a couple of examples where the parallel algorithm is not work efficient, but it's still better than the alternatives. So let's start with breadth-first search. And before that, I want to talk about other ways of traversing a graph. So why does the lecture start from graph traversals? Is essentially almost every algorithm does traversals of graphs several times, one after the other. So this becomes a building block for other algorithms. And let's start with depth-first search, which is the alternative way of traversing a graph. So I wrote a very simple recursive code on the right. You would never implement depth-first search with recursion because it's going to blow up your stack, but it's much easier to write it that way. So it's quite simple. You start with a vertex, and then you look at its neighbor, and you push that into a stack. So in a way, that will create a serial execution. So instead of looking at the other neighbors of 0, you will continue with the children of your children, and so on. So in this example, we will be numbering vertices from the source vertex 0 all the way to the end. And now this is where the depth-first search recursion hit all the way to the bottom end of the graph. And now the recursion will slowly roll up. And then we will actually get a chance to visit the other vertices. I haven't decomposed the tree associated with that. But essentially, that's the ordering it goes. So what might be the problem of this approach for parallel computing? I guess it's a little, maybe I shouldn't go over too much questions. The trouble here is this is an inherently sequential algorithm. There is no known way of parallelizing this algorithm without changing its fundamental nature of depth-first search. You get some sort of bounded depth-first search, breadth-first, depth-first mixes, but the very depth first search, the canonical depth first search is not amenable to parallelization. So the span of depth first search, meaning that the number of synchronization you have to do in the worst case is O(n), which is the number of vertices in the graph. So it's a pretty bad idea for trying to parallelize this. But it has been a very fundamental tool for designing linear time graph algorithms. So by giving up depth first search, we're actually giving up a lot of linear time graph algorithms. That includes strongly connected components and biconnected components we'll see later in this class. The parallel version, the more parallelizable graph traversal is breadth first search. So here's the difference. I guess the names are pretty explanatory. You're going to first explore all the neighborhoods, all the vertices that are one hop away from the source vertex before you go to any neighbors that are 2 hops away from you. So the output is really a numbering where all the neighbors that are 1 hop away gets a number 1, and all the neighbors that are 2 hops away gets a number 2, and so on. So this is a very important building block, and we'll see some of the applications today of breadth first search. For example, we'll see between centrality uses breadth first search. A new version of strongly connected component needs to use breadth first search, and some other algorithms that I won't talk in detail, such as bipartite matching and maximum flows, actually use breadth first search. So how do you parallelize this algorithm? It really depends on the graph. So the first and most widely accepted way of parallelizing breadth first search is what's called this level synchronous approach. Here, you explore in parallel all the neighbors that are 1 hop away from you and 2 hops away from you, and so on. So the number of synchronization points you do in this level synchronous breadth first search is the diameter of the graph, which makes it a good choice if you have a low diameter graph. The downside is if you have a high diameter graph, such as a graph where I would say even graphs from physical phenomena, like a 2-dimensional grid, square root of n is actually a pretty high diameter in practice. You wouldn't like to do so many synchronizations for an algorithm. So for those kind of algorithms where the diameter is high, or the road networks are actually high diameter too, relatively, there's an alternative algorithm which hasn't been studied very well in parallel. It's an algorithm due to Ullman and Yanakakis. So you choose a couple of super vertices in the graph, and you do path-limited searches from those. And then you stitch those super vertices together by running an all-pair shortest paths. It's fundamentally a much more complicated algorithm, and that's probably why it hasn't been studied too much. So in this class, I will mostly focus on the level synchronous approach, because there is a lot of exciting developments even in that area. So here's a performance observation. When you run a level synchronous breadth first search on a low diameter power law graph, this figure is what you get for, in a way, a trace of the algorithm. So the percentage of total work and the number of vertices in the frontier. By the way, I haven't defined frontier, so let me do that first. In a level synchronous algorithm, the frontier is defined as the current active set of vertices. In the first iteration, the frontier is 5, 7, and 2 in this graph, and 8 and 3 in the second iteration, and so on. The frontier and the number of vertices in the frontier and the execution time are pretty much correlated. But what you see here is, even though the algorithm takes 15 steps to finish, bulk of the work is in 2 or 3 steps, where most of the vertices are explored. And you'll also see that this is a very exciting development, this observation a grad student, fellow grad student of yours, Scott Beamer, has made a couple years back, where he looked at those graphs and said, here's the trouble with real-world power law graphs when you do a level synchronous algorithm. And he basically did it by looking at this trace. So let me show you, maybe go over the example in this case. So you want to start a breadth-first search from vertex 0 in the bottom right figure. And after the first iteration, you discover vertices that are numbered 1, that are 1 hop away from you, and now they become your frontier. And from there, you will explore the rest of the graph. Well, you'll see that all the unvisited vertices that are currently empty white balls, they have multiple vertices that are trying to claim them as their children. If you think about breadth-first search as parents finding their children. So what that means is only one of them will succeed, right? There are two yellow vertices here trying to discover one white vertex in most of the cases, in two out of the 3 of the cases. This is, of course, a minimal example that doesn't tell you the great complexity and how much you can say from this algorithm. But I assume the performance graphs will tell you. And on the right, the figure actually gives you a sneak preview about how much you can save. The dark blue triangle there is the successful discoveries made by the algorithm. The lighter blue is unsuccessful because you're trying to claim your peers, the ones that are in your level. And the dark golden color is all this unnecessary failed child examinations. So instead of this huge big triangle that covers everything, you can get away with just computing the dark blue triangle. So this is kind of surprising because the fundamental breadth-first search is linear time. And in the worst case, you can't do better than that. You can come up with graphs where linear time is the best you can do. But the world runs on algorithms that, in the worst case, might be bad, but they care about the actual practical cases. And this is one of those instances. So Scott nicely called this algorithm, the first he called it bottom-up, because if you look at the breadth-first search tree, it goes from bottom-up at some point. But it's a simple observation that you can't run this algorithm all the way from the beginning. You can't just say, let all the unvisited vertices, which is everyone except the root, try to find root, because you have the same problem. So essentially, you come up with a hybrid algorithm that does a standard level synchronous top-down approach until the frontier gets really big, where the failed child examinations start dominating. And at that point, you switch back from bottom-up to from top-down to bottom-up. And it's been neatly called the direction optimizing algorithm. So you can read the papers for the exact heuristic on how to switch back. But it's pretty robust in the sense that if you don't optimize it perfectly, it still is 5 to 10 times faster than top-down, regardless. The caveat here is there is a range of data, the graphs, that this optimization is amenable. And they're mostly, again, low diameter, power law-like graphs that you'll see in a lot of real instances. But as I said, high diameter graphs, it probably won't work very well. From now, I'll go over a little bit to how you can cast some of the graph computations into the language of linear algebra. You might find this interesting because this class mostly focuses on linear algebra. And I'll just give an example of breadth-first search, maybe to give you an insight about how this is done. So here I have a picture of a graph with 7 vertices, a directed graph, and the transpose of its adjacency matrix is pictured in the middle, I think. And every single dot there represents a non-zero, and meaning an edge, a directed edge. So in order to do breadth-first search from vertex 1, the simplest thing you can do is multiply the transpose of the adjacency matrix with a vector that only has 1 in it in the first location. So as you can see, after this multiplication, the output is your second frontier. you discover 2 and 4. Pretty neat. And then all you need to do is to transfer that guy, 2 and 4, to the right-hand side and do this multiplication again. And by doing this multiplication, you will discover the second hop neighbors. You will discover 3, 7, and 5. I will say you will accidentally rediscover 1 as well, which is why I colored it with a football color. I think maybe in this country it's a soccer ball color. But you can prune those out. It will discover the previously discovered vertices, but pruning them out is pretty easy. So this is how you do breadth-first search in the language of linear algebra, by doing just matrix, sparse vector multiplies. And why I talked about this is because now I'm going to talk about parallel breadth-first search algorithms based on one-dimensional decomposition and two-dimensional decomposition. And this will help you illustrate what I mean with one- and two-dimensional decompositions. So here's the one-dimensional version. As I said, you chop the adjacency matrix in one dimension. So here I'm chopping it with columns of the transpose, which really is rows of the original matrix. And the only reason I'm using transpose is because it's easier to draw column vectors than row vectors in slides. So this decomposition is very easy to visualize in the graph. You see that all the blue dots are essentially the adjacencies of 1 and 2. And all the red dots are adjacencies of 3 and 4, and so on. So the algorithm here to do one step of the breadth-first search is pretty simple. You would do only one piece of communication. First, you do find the owners of your current adjacency without any communication. Now everybody will discover lots of its neighbors. Now the neighbors need to update themselves because they have to tell who is the parent for each one of those. At that point, you have to do a communication. You do an all-to-all communication saying that, hey, I discovered this vertex, so I'm sending a message so that he updates himself. The downside is many other people might be discovering the same vertex. So there'll be lots of duplicate messages. You can put them in bulk, but essentially what you won't get away with is the all-to-all communication. So you'll do an all-to-all communication, and if that matrix was regular, meaning that all the non-zeros were on the diagonal, you wouldn't be doing all-to-all. But in many real graphs, you will be doing an all-to-all communication. And then the people who get the messages update their local data structures, and you keep going this way. The two-dimensional algorithm, by contrast, is fairly different. I guess this is a picture of the two-dimensional algorithm. So we chop the data adjacency matrix into a checkerboard fashion. And it's not extremely easy to figure out, as I said, what kind of edges are corresponding to what kind of non-zeros. But if you think about it a little bit, you'll see that there is an order in there too. Essentially, you're chopping the vertices into pieces of square root of n. And for every subset of those, you're rechopping its edges to another square root of n pieces. So there is an order in there. And that order helps the algorithm to be a little more structured than randomly distributing edges. Here we do 2 times communication. First, in order to do a local discovery, first of all, think about 1. Processor 1 owns vertex 1. Sorry, let me not call processors with numbers. The blue processor owns vertex 1. So it's responsibility to discover its adjacency, its neighbors. Luckily, it owns one of the edges that goes out of 1, meaning the edge that goes to 4. But it doesn't own the edge that goes to 2. Right? So its job is to gather that edge from 2 before it can do a local discovery. And that's the difference from the one-dimensional algorithm. Since we don't own the adjacencies of ourselves completely, we have to do a gather operation to get those. And then the rest of the algorithm is pretty similar to one-dimensional. So you can easily say that, hey, you just increased the amount of communication. So why would that be faster? Well, for 2 reasons it's faster. One of them is the amount of communication, if you actually analyze it empirically, went down. And now the communication, the gathering operation in the first step, only happens in one dimension of the processor grid. You're not doing an all-to-all communication. Instead of communicating with p people, you're only communicating with square root of p people, which I mean p as the number of processors. For 100, it doesn't matter, right? But for 100,000, it actually matters a lot whether you're communicating 100,000 people or 100 people. So both of these steps, the communication happens only on one dimension. And you'll see that, so here are the performance results of those things. And they have been substantially improved. But you'll see that the red ones are one-dimensional algorithms. And go ahead.
Could you explain the axes?
Yes, I will. Thank you. So these, of course, for both slots, the axes are different. On the left, the higher is better. It's the gigaTaps, which means the traversed edges per second. It's like a performance rate similar to flops, floating point operations per second, but a version that's tailored for graphs. On the right, the lower is better, where the y-axis is the communication time in seconds. For both cases, the x-axis is number of cores. That goes from 5,000 to 40,000. So that's a pretty big run. And it's actually running on a graph with billions of edges and vertices. And you'll see that the two-dimensional algorithms actually are both more regular in terms of performance. They don't do a lot of ups and downs like the one-dimensional algorithm, which is amenable to how much network contention happens in the all-to-all phase. And they're actually faster. And these days it's by a large margin, but I haven't rerun those numbers. How about you can say this algorithm discovered by Scott Beamer and his colleagues, the direction optimality? Well, you can actually put that algorithm together with the two-dimensional algorithm and get substantial savings over the previous one. So let me talk about the axes again. The y-axis is, in both slot graphs, is the search rate. Again, traversed edges per second, billions of traversed edges per second. And the top-down means the previous two-dimensional algorithm that I described. The hybrid one is when we combine that two-dimensional top-down algorithm to the direction optimal algorithm that I described a couple slides ago, where you switch back to bottom-up search from top-down. And the differences are drastic. You'll see that on the left, you see a scaling of a syntactic graph where the speed up can be 7 or 8 times more than the top-down, which was already faster than the one-dimensional algorithm. And on the right, you see a real graph of Twitter, where Twitter at the time didn't hunt down people for collecting their graphs. Nowadays, you can't run this experiment, I think. You can still use the old data, but you can't collect new data. And this is actually a substantially bigger run. The biggest run on the left uses 250 trillion edges and has a search rate of 200 billions of edges per second. So this is pretty much where the just doing algorithmic advances on a problem has taken us from the times where breadth first search used to take minutes or hours to something that it takes microseconds. Or milliseconds, maybe, depending on the graph. So that's so far for graph traversal and breadth first search. Now I'm going to shift gears and talk about more exciting stuff with probably more applications. And I'm going to start talking about shortest paths. I'll first talk about single source shortest path algorithms, delta stepping and fast, and then I'll talk about an all-pay shortest path algorithm. So what's the single source shortest path algorithm? Contrary to the conventional wisdom, it's not a path from one vertex to the other. It is a single source to every other vertex in the graph is considered a single source shortest path. So there are two famous serial algorithms for that, Bellman-Ford and Dijkstra. Bellman-Ford is what people call label correcting algorithm. And actually, this is a technical terminology, label setting, label correcting. And all that really means is when a vertex is settled, is finished, it will never be visited again. So that's the property of Dijkstra. Bellman-Ford doesn't have that property, so it keeps iterating until things converge. Every single vertex can still be active later. You can't say that this has been done. But the advantage of so the advantages and disadvantages is Dijkstra is much faster in serial than Bellman-Ford, but it only works on non-negative edge weights. And Bellman-Ford works on any graph unless there is a negative cycle. And at that point, shortest path is not well defined anyway. A fact is no known PRAM algorithm is work efficient and runs in sublinear time. That's fine. But in practice, there is a really good algorithm. We're going to talk a lot. It's due to Mayer and Sanders. It's called delta stepping, which can be considered as a middle ground between Bellman-Ford and Dijkstra, specifically tailored for parallelism in mind. And finally, I'm not going to talk about in detail. This is a very recent work where a bunch of people from IBM, Chakravarthy and Fabrizio Petrini and so on, combined delta stepping and the direction optimizing BFS approach. Not BFS, but the still direction optimizing approach to get a supercomputer scale single source shortest path algorithm, which does billions of edges traversed per second for this relatively more complicated problem. So what is delta stepping and why is it useful? So it's a label correcting algorithm, meaning that unsettled vertices are going to stay and you will need to relax them. You can define it as an approximate bucket implementation of Dijkstra. And the algorithm will degenerate into Dijkstra if the delta is really small, smaller than any edge weight in the graph. And it will degenerate into Bellman-Ford if the delta is really big. And it's actually unnecessary to try to explain these in text. You will have a much better chance of understanding it once you see the example. So the main operation is, I won't put it back again in the next slide. A relax of an edge, which I will refer a lot, is just updating the distance of its endpoint by its previous distance, or the distance that come to u and taking the weight of the edge from u to v. So essentially, is this edge decreasing the distance to v? If it is, then update it. So that's the relax operation. So here's the algorithm run. Essentially, in this algorithm, you pick a delta. In this example, we'll pick a delta. It's 0.1. And we will separate the edges, or vertices, two buckets. If it is delta far, at most, it's in the first bucket. If it is delta to 2 delta far, it's in the second bucket, and so on. So that will control parallelism, and so on. So the algorithm runs over phases until it converges. But each phase is also a while loop, which examines that particular bucket. So let's start with an example again. So at the initial phase, we start with the vertex 0. There is only one bucket. And we relax its edges. We will only relax its light edges, meaning that if it is an adjacent edge, adjacent vertex that is farther than delta away, we won't relax it immediately. And in this case, the edge that goes from 0 to 1 is a heavy edge. And the reason we're not relaxing it is we're trying to process all the vertices that fall into this current bucket. This bucket is distance 0 to delta. And even if we relax this edge, there is no chance that vertex 1 can fall into this bucket, because it's a heavy edge. Its distance will not shrink that far. So we only go over light edges and relax them, clear the current bucket. So maybe another iteration is going to help. Now we're at this, still we're in the zeroth bucket. The point is the vertex 2 fell within the distance of delta. So we're still in the existing phase within the while loop. So now we're going to examine the neighbors of vertex 2, but only the light edges. And we'll see that some of them put the neighbors into the same bucket, some of them don't. You know, for the ones that I put in the same bucket, we'll keep iterating until the bucket is completely empty. At which point, we'll see that the buckets are, the first bucket has been finished. And at that point, now we can relax all the heavy edges that we previously looked at, which were, for example, the edge that goes from 0 to 1 and so on. Now we can all relax them and find out what buckets they go into. And then we'll move on to the next bucket and start this while loop again. So every bucket is a phase. It's kind of a nice algorithm, and it has its advantage is really its tunability. You can choose a delta. And I think the IBM folks, what they did is they chose a dynamic delta, meaning that the algorithm towards the end degenerated into Bellman-Ford because it made more sense for performance. And you can do that too if you're clever about it. So you'll see that this is the number of phases the algorithm takes on the y-axis. And on the x-axis, there's a bunch of different graph families. So the algorithm takes a lot of phases for high diameter graphs, expected, right? And the weight, average shortest path weight, is also another determinant of the performance. So these two things combined determines how fast the algorithm runs, because its complexity is really linear on the number of edges and vertices, plus the diameter times the maximum shortest path weight, the length of the shortest path. I should have called length. Another update. So essentially, you can look at your graph and figure out whether this is going to be a good algorithm or not. And here's another exciting algorithm. This is called FAST, Hardware Accelerated Shortest Path Trees. This goes over a long research line of defining pre-processed vertices for graphs. And it is a nice intuition. So let me describe the intuition. When you're going from one place to the other, whether I'm starting here or going to San Francisco, or you start in Ashby-Bart, or somebody else starts in Albany, doesn't matter. All of us go to Highway 80 and we cross the bridge. So that's the intuition. At some point, you want to go to the highway. So they define a hierarchy of nodes based on their highway dimension. Now, you can't know by looking at the graph which one has the highway dimension. It's finding that is not an easy problem. But the correctness of the algorithm is not wrong. What that really means is, if I redefined Highway 80 to be something else, as long as there's a path, I will still find a route. It would take longer. That's all. The correctness doesn't change. It's just the algorithm takes longer to run. But there are heuristics to find the right highway dimension hierarchy. So this is an introduction slide. What do you do when you define the hierarchy? So there is a pre-processing phase in this algorithm before you start doing any computation. And this pre-processing is to add shortcuts between the highway locations. So here's an example. Let's say we found the correct order of importance based on the highway dimension of nodes. And the input, and we numbered every vertex with that. So I'm referring to the top left figure, the first figure. So we ordered all of the vertices, 1, 2, 3, 4, 5, 6, 7. First, we will eliminate the first vertex, which really means this. We'll say, hey, this guy's highway dimension is the lowest. What it means is now we have to make a shortcut from its neighbors. It has only two neighbors, which is 5 and 4. So we add a shortcut from 5 and 4. It says, if I were to go from 5 to 4, I would take distance 3. And I will do this for every single one. I won't go into one by one, but the next step, I'm going to eliminate 2, and then I'm going to eliminate 3. And after you have done that, this is the graph I get. This is the same graph after I eliminated every one of them. You know, I eliminated 2, I eliminated 3, and added another shortcut between 4 and 7, and so on. And I eliminated 4, I added a shortcut between 5 and 7, and so on. So once the pre-processing is done, you'll see in real road network, there is an increase in the number of edges. It's not too bad. In practice, it's 75% increase. I'll come to the cases where it might be really bad and why this is the case. But for road networks, it's pretty OK. So why did we do that? Well, here's the advantage. When I try to find the shortest path from a vertex, let's say S, numbered 4, I don't need to look at 1 or 3. I've already added shortcuts. I know if I had to go from 4 to 7, and if I had to take 3, you know, I know what the length of the shortcut is. I already pre-computed it. So all I need to do is do an upsweep, which is target independent, because I'm always going to the highest highway dimension regardless. And that's a nice property. So I'm doing only an upsweep. And the top-down sweep is even more interesting, even though it's target dependent, because I'm trying to go to, no, it's actually target independent too, because I'm trying to find all the shortest path to every other vertex. It doesn't have a destination. And it can be computed without a priority queue. And so it really means you're still doing the relaxation operation, you know, setting du to the minimum of du and dv plus the edge, v and u, but you don't really need to do a priority queue. A linear scan is correct, and you have to look at the paper to convince yourself that's the case. So what is the advantage of having this in a linear scan as opposed to using a priority queue? A priority queue is essentially a hard-to-parallelize data structure, because there is always the smallest entry, and you want that smallest entry. And how do you parallelize that is a completely problematic problem people have been thought about years. So the linear sweep gives you the advantage that you can parallelize this on GPUs, on distributed memory machines. It becomes a data parallel problem. And here's what it means in practice. So you see the runtimes of running Dijkstra and fast on the road networks of Europe and USA. And all of them are in seconds. So you should probably care about the first column there is from 100, you're going from 1,000 to 19. And the second column of device is really what kind of device this is running at. It's a different machine. You should be comparing, for example, the row that says M14 to the row that says M14. And that's the same architecture you're running the problem on. And you see that there is almost a over 50 times speed up observed compared to Dijkstra. And that's a fast Dijkstra implementation. This is not a textbook implementation that they have done. And I said you can actually port this thing nicely to the GPU because it doesn't require a priority queue. Although it's a different architecture, you'll see that the runtimes are even lower. So that works. But I said there is a caveat, that there is this point where you're introducing fill. Jim, did they see sparse Gaussian elimination by any chance?
Briefly, we talked about it.
So you might have heard in the previous lectures, and Jim said briefly, I don't know what that means. So every time you eliminate a variable in sparse Gaussian elimination, you're introducing fill. So you're destroying a little bit of sparsity. That's very similar to what's happening there. And the road networks, it works fine, because road networks are almost planar, except for the bridges that goes there. You can actually draw it otherwise. What that means is you can bound the fill that's going to happen during that ordering phase. And you would know from the planar separator theorem that there is a square root of n separator. And you can bound the field pretty nicely using that theorem. What that says is this algorithm would probably not work on graphs that doesn't have good separators, like social networks wouldn't run very well, and there will be so much fill that all the advantages of getting linear sweep are lost. But it's a good algorithm on where it works. OK, so far we've talked about single source shortest paths. Let's talk about all pair shortest paths. As the name implies, the problem is now to find the least cost paths, like the minimum length paths, between every pairs of vertices in the graph, as long as they're reachable. And the standard algorithm to do that is a triple nested loop that looks awfully like matrix multiplication, where you do an induction over k and do rank 1 updates, and essentially relax all the vertices. You can't reorder the outermost loop, so that needs to be k, but you can reorder the innermost loop. And at every iteration of k, the outermost iteration, what this algorithm finds is all the shortest paths between every pairs of vertices that go through intermediate vertices up to vertex k. So it won't find the shortest paths if it touches vertex k plus 1. So that's the induction sequence of dynamic programming. But that's outside the scope of this lecture, why this works. But to motivate you why this problem is useful is not only in graphs, it actually is useful on data analysis too. One of the most highly used nonlinear dimensionality reduction algorithms, probably the most cited papers, requires one to run all pair shortest paths between every pairs of data points before it does the dimensionality reduction. So there's a lot of applications beyond this, and metric nearness problem is one. So you can think of applications that are beyond roads and social networks for this problem. But for parallelization, I'm going to talk about a different schedule of Floyd-Warshall, which we call the Clean's algorithm, but the name is not that important. So it's still the same updates as Floyd-Warshall, but it does it in a very different schedule, in a recursive schedule. And so the whole algorithm is listed in this box on the bottom right side. So the first you do a recursive call in the lower top, the top left quadrant, and then you do 2 matrix multiplies and another matrix multiply to update the bottom right quadrant, do another recursive call, and so on. So why does this make sense? This makes sense because when you think about what kind of paths you've constructed at the end, you will verify that it's actually visiting every possible path that needs to do. And the proof is based on splitting the vertices into 2 sets, V1 and V2. And now the edges in the top left quadrant A correspond to all the connections within V1. D quadrant corresponds to all the connections within V2. And B and C corresponds to across division connections. And you'll write the regular expression that describes this final output, and you'll see that that's the shortest path. The caveat here is it's not a standard matrix multiply. For every single scalar addition, you're using a minimum operation, and you're overloading the scalar multiplications with an addition operation. So that's the so-called min plus semi-ring. You'll run this algorithm. And I don't know if it's relevant, but here's a short execution of the algorithm for the first couple of phases. And the only purpose of this slide is that it will not only construct the distances, if you overload the operations properly, you will get the paths themselves as well, if you care about them. In general, for the data analysis applications I talked about, you don't need the paths. You just want the distances. Excuse me. So what does it buy you? So this is an old slide, circa 2009, I think, of a work I've done when I was a grad student. As if you implement the naive Floyd-Warshall algorithm on the GPU, a very powerful device at the time, is you'll get the performance that is the solid red line on top. So this is a log-log plot, and the y-axis is the milliseconds. So the lower is better, and the x-axis is the dimension of the problem. And if you do it recursively, you first get the red line, and then if you use the fastest matrix multiply available on the GPU, you get the purple line. The difference between doing it naively and using this algorithm that's rich in matrix multiplications is a factor of 480. So it kind of makes problems that are ridiculously expensive to doable. And we leveraged on this idea of this recursion and developed this communication avoiding version in distributed memory. So you'll see that there's one challenge on implementing this algorithm in distributed memory, and it's the recursion. Because here we are recursing on a subset of the matrix. But the data distribution is so that you have to make a decision whether you will have all the processors working on that subset or just some subset of the processors working on that subset and let everyone else do something else. So that's the decision you take when you're parallelizing the recursive algorithm on distributed memory. And there's an optimal point to switch from that, what we call the cyclic step, where everybody works on the whole problem, on the subset of the problem, versus some processors don't recurse on that sub-problem. And that's what we call a block step. And there is an optimal point where you have to swap between cyclic step and block step to get the lower bound on bandwidth and latency. So that's how you handle the recursion. And the point about communication avoidance comes from matrix multiplies. Since it's rich in matrix multiplies, as you strong scale the problem, did you talk about communication avoiding algorithms at all? Yes. So you would know all of those. As you strong scale the problem, there is a lot of unused memory in the processor. So then you can capitalize on those to make copies of the input set on the matrix multiply and get these figures where, again, this time the higher is better. It's the flops rate. And the blue stacked bars are if you don't use any replicas, no communication avoidance. So you'll see with the increasing number of nodes, the algorithm will start slowing down due to the number of synchronizations. For the small data set and for the larger data set, it won't speed up as nicely as you would want. But however, since we have more memory, we can actually replicate and get the first yellow curve and the red curve, and nicely scales up. So far, so good. All right. So I have about 17 minutes. But I think I'm in a good place. Between centrality is an important problem, but there is not much to say about it except that it's a nice application of breadth-first search. So just to give you a nice application of breadth-first search, between centrality finds the influential nodes in a graph where it ranks them based on how many shortest paths are passing through them. So the definition of importance there is, if I'm an important node, I should be connecting people, right? And then if I calculate all the shortest paths and the majority of them are passing through me, I'm an important node. That's the intuitive definition. And there is a nice algorithm called Brandeis algorithm that will calculate it in a sparse graph without doing all pair shortest paths. It just does a smart breadth-first search with a different kind of update. And that's the high-level idea, which I won't go into much detail. Both the algorithm does a forward step and backward step, and both of them are essentially breadth-first searches. One of them is a forward breadth-first search, the other one is a backward breadth-first search. And instead of keeping a value, you will need to keep multiple values for every vertex. So you will need to keep, instead of a single parent, you will need to keep all the parents. And the reason for that is because if there are multiple paths going through that vertex, you would need to accurately normalize it. So you need all the paths that are going through you. So it's a perturbed breadth-first search. Level synchronous approach still works. And the accumulation step is, again, a backward breadth-first search, as I said. Probably can go over the details on the references cited at the beginning. But instead, I actually want to say something a bit, yes.
Does bottom-up work?
Bottom-up, yes, bottom-up is essentially a level synchronous algorithm. It would work, but I haven't seen people applying it so far. That's because academia. Somebody will say it's trivial and won't let you publish it. But I want to say something a little different about this distributed between a centrality. As you can see, I said between a centrality is an application of breadth-first search. But you have to do breadth-first search from every single starting vertex for the final accurate between a centrality. So it's extremely expensive. The good thing is you can sample some subset of vertices and do just breadth-first search on them. And it would be a good representation of the final between a centrality score. It's called an approximate between a centrality. That's nice. So you need to do a breadth-first search from every starting vertex. How do you parallelize this really nicely? Is actually a primitive that some of us has worked, including myself and Jim, is a multiplication of a sparse matrix with another sparse matrix. So this time, the right-hand side matrix is a tall and skinny matrix. So what you do here is this allows you to do parallelize breadth-first searches from multiple starting vertices. I already showed you how to do breadth-first search with this picture. Now it's only a bunch of right-hand side stacked together. Nothing changes except that this algorithm encapsulates 3 different levels of parallelism into one operation, and you don't need to think about them yourself. So the columns of B essentially encapsulates the parallelism across breadth-first searches. Like 3 different starting vertices, there will be 3 levels of parallelism here. In practice, there'll be thousands of starting vertices. The columns of A transpose and the rows of B will parallelize over the frontier vertices. Whatever the size of your frontier, there's parallelism across those, and that's going to parallelize that. And finally, the rows of A transpose will parallelize over all the neighborhoods on that frontier vertices. Remember, if there are 20 vertices in the frontier, they probably have hundreds of vertices that are neighbors of them, and that's that parallelism. So you won't need to do anything about it. You just need to learn a good way of parallelizing this. And although I haven't cited here, I think we know a good communication avoiding way of doing it. So I have only 2 more things to go over, and they're very light algorithms. One of them is maximal independent set due to Michael Luby. So what's a maximal independent set? That's a good application of randomization and parallelism. So a maximal independent set is a set of vertices who are not neighbors of each other, and you can't increase that set by adding another one. This doesn't mean it's maximum, which means there might be another independent set that is of higher cardinality. But the only thing maximal says that if you give me that set, I can't increase it by adding another vertex. That's all it means. So for example, 4 and 5 is a maximal independent set, but it's not maximal. There is a better solution. But it doesn't matter in practice. In many cases, maximals are good enough. The algorithm to do this in sequential is extremely easy. You just start with a vertex, in this case 1. You look at its, you loop over all the vertices in this for loop. And if those vertices don't have any neighbors in the independent set, you just add them to the independent set. So you add 5, you add 6. At that point, all the vertices that are remaining has somebody adjacent to them that's in the independent set. You can't increase it. Super easy, but it's not really parallelizable. It has a span of ON, so you need to go sequentially. How Luby fixed this problem is to use randomization. And this works. There's better algorithms that does maximal independence set these days, but it's still the one that's most highly used in practice because it works in shared memory, distributed memory, blindingly fast. Everybody tosses a coin and comes up with a random number, right? And they look into their adjacency. they look into their neighbors and figure out if they are the minimum. They have the minimum random number among its neighbors. If they have the minimum random number, and you'll see if 1 and 5 will have that. And surprisingly, you can have bad luck. And so 5 has 4, but 4 has 1, and 8 has 4. So this kind of creates a dependency that you can't choose anyone on that list in the independent set. But the algorithm iterates. In the next iteration, it will toss a good coin, and it's going to converge. So the theorem is, of course, it's stated much more mathematically precise than how I wrote it. It's very probably is going to finish within log n rounds. So all that means is the span of the computation is now log n. It's not work efficient because it's doing, in the worst case, a factor of log n times more work. But that's OK. It runs much faster than the serial code in parallel. So that's an application of randomness. And here comes an application of recursion. So this is strongly connected components. A strongly connected component of a graph of a directed graph, it's only defined in directed graphs, is a component where every vertex can reach to every other vertex. That's all. And the fastest way to do this is in serial is to use depth first search that we talked in the beginning. But we know that it's not parallelizable. It has a bunch of applications, so we really want to parallelize this. For example, permuting permuting matrices to block triangular form is one of the applications in scientific computing. So these are already I've talked, but here's the super cool idea based on divide and conquer. And this is originally due to Fleischer, Hendrickson, and Panache. This is the best picture I could find that describes this algorithm is this little picture on the right. But essentially, you pick a pivot, a random vertex in the graph. Doesn't matter which one. And you find its forward set, which means the set of vertices that are reachable from that pivot. You do a breadth first search. And you find the backward set, all the vertices that can reach to this vertex. You do a backwards breadth first search. You change the orientation. OK, the intersection of this set is unique. And it's a strongly connected component. It is exactly the strongly connected component. So you found one strongly connected component. But you also found something more interesting, which means once you subtract that unique strongly connected component that is at the intersection of the forward and backward set, from the forward set, it's a set that is completely separate from the set of the backwards difference from forward. So let me rephrase it. What this means is by finding the strongly connected component from backward and forward algorithm, you essentially divide the remaining graph into 3 components. And one of them is the difference of forward set with backward set. One of them is the backward set and forward set. And the other one is all the remaining guys. And if there is a strongly connected component in the rest of the graph, they belong to one of these 3 sets. They don't belong to an union of those sets. They definitely belong to a unique one of these. And that's the fundamental theorem that lets this algorithm recurse on A, B, and C at the same time and increase parallelism that way. That was faster than depth first search. The downside of this algorithm is actually in real-world graphs. Again, you have to look at your data to understand what the problem is. The original implementation was you do a breadth first search by the random vertex you picked up, and you find a strongly connected component. Nobody thought that that strongly connected component can be as big as the graph itself, which sometimes happens because the real-world graphs have this giant strongly connected component that occupies more than half of the vertices in the graph. So for finding that efficiently, you need to use the parallel breadth first search techniques that we've described previously to get the span down to the diameter. So that was good. That's a solution. And the second problem was, in real-world graphs, the remaining strongly connected components, other than the giant one, are a lot of small ones. So the recursion keeps going and going for no good reason. And there is this smart idea of finding the weakly connected components and processing them in batch together so that the span doesn't go high. And that's a recent finding. It was a supercomputing paper last year by folks from Stanford. And it was a nice read, to be honest. You can take a look at it. So let me wrap up in the remaining 5 minutes. I guess I will list about the challenges in getting good performance. So parallelism is something we study theoretically. It's nice. But if your algorithm doesn't beat the serial algorithm, it's hard to get adapted. That's essentially the problem. So you have to know about the real-world factors that affect the performance. And one of them is the locality. You will need to actually increase the locality of your problem as much as you can. And here, essentially, is what happens to the performance as the problem size increases. That's a very typical curve you've seen in other matrix multipliers and so on. The performance rate drops significantly as the problem size increases because you're falling out of cache. So you have to do smart tricks to increase the locality in the problem as well. The parallel scaling problem is a little more interesting. The locality advances lumps entries of the graph together. And that is in loggerheads with the techniques that you use for parallelization. How do you parallelize for good load balance is you scatter everything out so that things fall out nice and evenly. Well, that destroys all the locality. So you have to find a good balance where you don't destroy all the locality, but you still get some sort of good load balance. And another thing is search for the most work-efficient algorithm. The work-efficient algorithm is a noble one. But in practice, if you can't find one, don't get stuck on it. An n log n algorithm is OK for a linear time problem sometimes. So this is a general picture about all the things you want to. So all the locality problems, all the data size, and the work performed. And in this whole three-dimensional domain, you're trying to find the best combination of those. Essentially, that's all I want to say. I'll use the 3 minutes.
Any questions for the speaker? Can you go back to the previous slide? So
This one or the?
So you're saying stream life is the best locality?
Not at all.
That's where all the data comes in?
Oh yeah. Well, it is not.
So stream life meaning all the data just flows in, you see everything.
Well, it is the best spatial locality. So I think this slide should be amended by me to say spatial locality explicitly. So it's not about temporal locality, because the other way around, the other extreme is random access at the top. So it doesn't have any spatial locality, and that's really going back to the case of falling out of cache kind of thing.
So one more question, which is if somebody wants to just use the best available code without writing it themselves, where do they go?
Depends on their concurrency. If they want an algorithm that runs on their GPUs, they probably browse NVIDIA's website for a good package, a Trust library or something like that. If they're running on their desktops, they might use Boostgraph library or something like that. If they want to run on distributed memory, they might come talk to me.
So the combinatorial blocks, is that the name of the thing you look at on your website?
That's right.
Okay. Great. Well, thank you again.
Thank you, Jim.